Myself Payal Joshi. I have completed my BSc with physics. Just imagine you are shaking hand with a person and suddenly you both get destroyed with a boom and release a huge amount of energy. Sounds crazy, right? How can it possible? But that may be the case if the person shaking hand with you is made up of antimatter. So let's focus on such a dangerous thing called antimatter, the mirror image of matter. Here is the outline of the presentation. First topic will be the discovery of antimatter. Second topic will be difference between matter and antimatter. Third topic will be matter-antimatter asymmetry. Fourth topic will be antimatter in nature. And the final topic will be artificial production of antimatter. So let's start with the discovery of antimatter. Curiosity of human mind and efforts of great scientists led us to the understanding of the fundamental building blocks of our universe. Basically, we all know that every object in our universe is made up of atoms. Atoms consist of proton, neutron, and electron. Proton and neutron are consist of quarks. In the most abstract form, this understanding of fundamental building blocks of our universe is named as the Standard Model of Particle Physics. It's a remarkable and elegant encapsulation of indivisible, extremely small particles. It includes six quarks, namely up quark, down quark, charm quark, strange quark, top quark, and bottom quark, and six kinds of leptons, namely electron, muon, tauon, electron neutrino, muon neutrino, and tauon neutrino. Standard model also includes forces that governs the behavior of the particles, like how particles move and interact, how particles bind together to give shape to the world. Up and down quark forms proton and neutron. Proton and neutron combines to form the nucleus. Proton and neutron are attracted by strong force by exchange of gluons. Strong force influences all the quarks. Electrons are bound to nucleus by electromagnetic force. They attract each other by exchange of photons. Electromagnetic force influences all the charged particles. Weak nuclear force is responsible for nuclear decays by exchange of W and Z bosons. Almost all fundamental particles are influenced by weak force. There is one more fundamental force which is of course gravity. It influences all the particles which have mass, but we still don't understand the role of gravity in microscopic domain. There is one more particle called Higgs boson, the God particle, which is responsible for giving mass to the particles. So this is the complete picture of standard model of particle physics. That's all. This is the recipe to create our universe. But once upon a time, we encountered an equation which said that what we know is only the half truth, and the other half was still in the black box. In microscopic domain, the behavior of tiny little particles can be described by the laws of quantum mechanics. And at very high velocities, we have special theory of relativity to describe the behavior of the particles. But in 1928, a brilliant British physicist, Paul Dirac, was wondering, what if microscopic particles like electrons moves at relativistic velocity? In short, he was combining quantum mechanics and special relativity, and what he found was an equation which nowadays known as Dirac equation. Here is the Dirac equation. I represents imaginary number gamma mu, polymatrices. Del mu derivative in 4 dimensions. M represents electron mass and psi is our well-known electron wave function. The equation got two solutions. The equation was working absolutely fine for electron. But what was surprising about the equation is that it was also worked well for positively charged electron. And the equation was so beautiful that Dirac firmly believed that somewhere in the universe there exists positively charged electron. And he was right. After 4 years of Dirac prediction, we got the first ever evidence of antimatter. On 2nd August 1932, Carl David Anderson discovered the positively charged electron, for which he won the Nobel Prize in Physics in 1936. Positron was the first evidence of antimatter and discovered when Carl Anderson allowed cosmic ray to pass through a cloud chamber and a lead plate. Particles, according to their charge, bend in different directions due to the influence of magnetic field surrounding the cloud chamber. Positively charged particle turns one way and negatively charged particle on the other. The track of positron appeared to be identical to that of electron, but in the opposite direction. Here you can see the photograph of positron track taken by Carl Anderson. The second image is here for comparison, which shows the electron spiral path in magnetic field, which clearly shows that the direction of electron and positron track are opposite. So, the experiment confirmed the existence of anti-electron. Let's move to the next topic, difference between matter and antimatter. So, what is the formal definition of antimatter? Well, antimatter is the material composed of the antiparticle of corresponding particles of ordinary matter. For example, ordinary hydrogen atom is made up of one proton and one electron, while antihydrogen atom is made up of one antiproton and one positron or anti-electron. For every particle, there exists a corresponding antiparticle. A particle and its antiparticle have the same mass, but properties such as electric charges are different. For quark, there exists antiquark. For proton, there exists antiproton. For neutron, there exists antineutron. For electron, there exists positron. And for neutrino, there exists antineutrino. Now the question is, how particle differs from its antiparticle? That's an interesting question. So let's see. Proton consists of two up quark and one down quark. Similarly, antiproton consists of two anti-up quark and one anti-down quark. Proton has net positive charge. Antiproton has net negative charge. Neutron and antineutron are both neutral particles, but their internal structures are different. Neutron consists of one up quark and two down quark. Antineutron consists of one anti-up quark and two anti-down quark. The most interesting case is the difference between neutrino and antineutrino. They both are chargeless and they do not have any internal structure. So how can we differentiate them? Well, to differentiate them, there is a property called helicity, according to which the direction of momentum vector of neutrino can be found according to left-hand rule from its spin direction, while the direction of momentum vector of antineutrino can be found from right-hand rule from its spin direction. What happens when a particle meets its antiparticle? Well, then they destroy themselves mutually. They annihilate. For example, when electron meets positron, they annihilate with the release of pure energy. Similarly, one gamma photon of sufficient energy can be converted into one electron and one positron. This reaction is called pair production. Both the reaction takes place according to Einstein's equation E is equal to mc square, which states that energy can be converted into mass and vice versa. But from these two reactions, we can conclude that energy can be converted into equal amounts of matter and antimatter and vice versa. Now, let me introduce you to one of the greatest unsolved problems in physics, matter-antimatter asymmetry. We all know about Big Bang, the birth of the universe. So how was the universe after 10 raised to minus 36 seconds of Big Bang? Well, at that moment, universe consists of rapidly expanding fireball of intense energy. Matter does not yet exist. After 10 raised to minus 32 seconds of Big Bang, matter and antimatter condense from pure energy. There should be equal amounts of each, according to Einstein's equation. In the interval of 10 raised to minus 32 to 10 raised to minus 6 seconds, frequent collisions, pair production, and annihilation between particles and antiparticles took place. And after 13.7 billion years after the Big Bang, the result is known universe, where billions of galaxies made up of only matter exist. Strange. If there were equal amounts of matter and antimatter in the early universe, then at this moment, 13.7 billion years after the Big Bang, our universe should look like this, completely empty. But the universe looks like this, and almost all the stuff in our universe is made up of matter. So the questions are, what happened to antimatter? Was more matter produced than antimatter? If yes, then why? If no, then where is the missing antimatter? Are there whole antimatter galaxies far away from our universe? Well, these questions have no precise answer. But if we work out what the universe was like 1 billionth of a second after its birth, it turns out that for every 1 billion particle antiparticle pair, there exists only one extra particle. And that is sufficient to create the matter world which we see today. If we can explain why there is one extra particle for every billion particle antiparticle pair, then we can explain matter-antimatter asymmetry. And if we can explain why that one was particle and not antiparticle, then we can explain the matter dominance of our universe. The matter axis of our universe is referred as baryon asymmetry, and the process which is responsible for the asymmetry is called baryogenesis. In 1967, Andrei Shekharov listed three conditions necessary to explain the asymmetry. First condition is the violation of baryon number, which requires that in the early universe there should be more baryon or matter constituent than antibaryon or antimatter constituent. The second condition requires violation of charge and charge parity symmetry. In simple words, under charge and charge parity transformation, the laws of physics should be at least a bit different for matter and antimatter, or nature should be somewhat biased toward matter. The third condition is the absence of thermal equilibrium in the early universe. Till now, we don't found any process that precisely fulfill these three conditions. But to explain the asymmetry, this condition should definitely satisfy. Although the world around us is full of matter, there is a very little amount of antimatter present in our universe. Let's see, where did we find antimatter in nature? Antiparticles are created everywhere in the universe where high energy particle collisions take place. High energy cosmic ray impacting Earth's atmosphere produce minute quantities of antiparticles in the resulting particle jets, which are immediately annihilated by contact with nearby matter. Satellite experiments have found evidences of positron and few antiprotons in cosmic rays produced by cyclic process at high energy. Electron-positron pairs may be sheared from the surface of a rotating pulsar or anything else. Preliminary results from alpha magnetic spectrometer show that positrons in cosmic rays arrive with energies that range from 10 gigaelectronvolt to 250 gigaelectronvolt. In September 2014, new results were published in Physical Review Letters in which positron fraction up to 500 gigaelectronvolt was reported. This result on interpretation have been suggested to be due to the positron production in annihilation event of massive dark matter particles. the year 1970, gamma-ray detectors flown on balloon discovered a huge cloud around the center of Milky Way, radiating gamma rays of energy 511 kiloelectronvolt, which is similar to the energy of gamma rays that are produced when electron and positron annihilate each other. So the question is, where does this antimatter come from? From earlier results using less data, the positron cloud seems to be spherical and centered on galactic center. Such a shape and position correspond to the expected distribution of dark matter. So it was suggested that dark matter was decaying into pairs of electron and positron, which then annihilate to produce gamma rays. The trouble with this idea was that dark matter particles needed to be much less massive than the theoretical prediction. So what's wrong? The integral satellite discovered that the antimatter cloud is not perfectly centered on the galactic center. The shape of the antimatter cloud was somewhat like this. Certain system of binary stars found to be distributed in the same manner. The black holes or neutron stars in the binaries are stealing gas from their companion stars, just like this. And when this gas falls into the remnant, it heats up and emits X-rays. It can estimate that this antimatter is coming from the X-ray binaries. Besides the observation of antimatter in nature, antimatter has been artificially created at particle accelerator like Large Hadron Collider in minute quantities. In 1965, a group of researchers reported production of nuclei of antideuterium at the proton synchrotron at CERN. In 1995, physicists at CERN announced that they had successfully created the first atom of antihydrogen at low energy antiproton ring. It was a very big achievement, but the atoms were too hot to study them. So the challenge was to slow them down. In the late 1990s, antiproton decelerator was established, which provided slow, low-energy antiprotons for antimatter experiments such as Athena, Atrep, and Alpha. Athena was the first research project or experiment to produce 50,000 low-energy antihydrogen atoms, as reported in Nature. Atrep was the similar experiment to compare hydrogen atom with antihydrogen. In 2002, Atrep provided the first glimpse inside the antihydrogen atom after researchers used cooling process to slow antiprotons down so that they can be studied. Alpha was a successor of Athena, set up in 2005. Alpha mixed, captured and studied atoms of antihydrogen and compares them with hydrogen. On 26 April 2011, Alpha announced that they had trapped 309, I repeat, 309 antihydrogen atoms for nearly 17 minutes. This was the longer than neutral antimatter had ever been trapped before. Alpha had used these trapped atoms to initiate research into the spectral properties of antihydrogen to compare the spectral properties of hydrogen and antihydrogen. Alpha confines antihydrogen atoms in a magnetic trap to avoid any contact with matter and then measure their response to a laser frequency corresponding to a spectral transition in late 2016. The collaboration used this approach to measure the frequency of 1s-2s transition of antihydrogen with a precision of 2 into 10 to minus 10, finding a good agreement with the equivalent transition in hydrogen. So the experiment confirmed that the spectral properties of hydrogen and antihydrogen are identical. In 2018, Alpha used several detuned laser frequency with slightly less than and slightly higher frequency than the 1s-2s transition frequency of hydrogen, which was 243 nanometer. This allowed the team to measure the spectral shape of the 1s-2s transition of antihydrogen and to get a more precise measurement of its frequency. The shape of the spectral line agrees very well with that expected for hydrogen. So again the experiment confirmed that the spectral properties of hydrogen and antihydrogen were identical. It is clear that with one positron and one antiproton we can create antihydrogen. You think it's not a big deal, but believe me, it's a really big deal because we are surrounded by matter and matter immediately annihilate antimatter. To give you an insight, here is the basic process of making antihydrogen. The first step is that electric and magnetic fields holds the antiproton separate from positron in a near perfect vacuum. The second step is that the antiprotons pass through a dense gas which slows them down further. Third step is that low energy antiprotons are nudged into the cloud of positron using electric potential. And the last step is the two types of charged particles combine to form low energy antihydrogen atoms. The most compound nuclei observed till now in our universe is anti-helium. Anti-helium-3 nuclei were first observed in the 1970s in proto-nuclear collisions experiment at the Institute for High Energy Physics by Y. Prokoskin's group and later created in nucleus-nucleus collisions experiments. In 2011, Star Detector reported the observation of artificially created anti-helium-4 nuclei from such collisions. So good, so far. We are capable of producing antimatter. Antimatter seems to be a brilliant source of energy as it converts 100% of its mass to energy. But the biggest limiting factor in the large production of antimatter is the unavailability of antiprotons. Data released by CERN in 2010 states that when fully operational, their facilities are capable of producing 10 million antiprotons per minute. Assuming a 100% conversion of antiprotons to antihydrogen, it would take 100 billion years to produce just 1 mole of antihydrogen. Here is the trap used to combine positron and antiprotons to create antihydrogen atoms. There is one question for you. What is the most expensive material you can think on Earth? Gold, diamond, platinum? Well, not really. The most expensive material known to humanity till now is antimatter. Scientists claim that antimatter is the costliest material to make. In 2006, Gerald Smith estimated $250 million could produce 10 milligrams of positron. In 1999, NASA gave a figure of 62.5 trillion per gram of antihydrogen, which is equal to 83% of global GDP to produce just 1 gram. This is because the production and preservation is very difficult and because we are surrounded by matter and antimatter immediately annihilate each other. The most powerful nuclear weapons can convert 7 to 10% of their masses into energy, while matter-antimatter collisions converts 100% of its mass into energy. So how dangerous is antimatter? The reaction of 1 kilogram of antimatter with 1 kilogram of matter would produce 1.8 into 10 raised to 17 joule of the energy, which is roughly equivalent to 43 megatons of TNT or slightly less than the yield of the 27,000 kilogram Tsar Bomba, the largest thermonuclear weapon ever denoted. Can you imagine the blast when 1 kilogram of matter meets 1 kilogram antimatter? Maybe something like this. Besides the great mysteries of antimatter, there is one more question that immediately arises. In future, if we can create antimatter in large amount, then will it be a boon or curse? God knows. Here is the list of references I have used to make this presentation. I am thankful for Hariam Vatsal for giving this opportunity. I hope you enjoyed. Thank you for your attention.